Now, once we understand, we reviewed sinusoidal functions, and we wanted to look at the connection between this chapter and earlier chapter in chapter 7, the transient circuit. Remember what we did in chapter 7? We want to solve a problem that involves inductors or capacitors and resistors. We need to solve we need to solve differential equations. And we wish not to do that. So we wanted to establish a way of we need to establish a way of solving that type of problems without going through differential equations. So here we wanted to use the example, RL circuits, very simple RL circuits, only 2 elements. We wanted to see how we want to do that transition to not to solve the differential equations, to solve the problem. So what we have done for this problem is that we look at this simple single loop circuits. We can just simply apply KVL. What do we end up with? And we're going to say, let's define a current going through the circuits I. And we see remember the passive sign convention always applies. So we will have the voltage across the inductor is L di dt. And the voltage across the resistor is R times I. And that has to be equal to voltage given by the source, which is Vm times cosine omega t. Now, looking at this differential equation, again, we can imagine, we can guess what kind of solution that would most reasonable. That we had the derivative of this omega I, the current here, and plus the current itself and multiply a constant. And yet that would have to be equal to some kind of sinusoidal function. So that's very reasonable to assume or guess that IT should have a form of sinusoidal function as well. So we say, well, we don't know the amplitude. We're going to just assume A. Whenever the amplitude is, we need to figure that out. But it should be some kind of sinusoidal function. Now we're going to say that should be also some kind of cosine function. But we definitely cannot assume that the phase angle of the current is the same as the voltage. So we're going to have to assume that is omega t and plus some kind of phase angle that we don't really know. We need to figure that out. Now, from there, we can also write this as a different form. If we remember another set of trigonometry identities, which I'm going to use a green. I'm going to write it here. That is a sine. If we have a sine alpha plus beta, we can split that up. That is equal to sine alpha times cosine beta and plus cosine alpha times sine beta. Now, what if we have alpha minus beta? That equation have the same form except it's minus. And for the cosine, we also have a similar form. This is if we have a cosine alpha plus or minus beta, that will be equal to cosine alpha times cosine beta minus plus sine alpha times sine beta. This is a third set of trigonometry identities that we're going to use frequently. So now we're going to apply it here, that we have a cosine alpha, that will be the alpha that we're referring to in this identity here, and the phi would be the beta. That's going to be beta, this is going to be alpha. So we're going to say this is equal to a times of cosine alpha, which is omega t, times cosine beta, which is the beta is phi, and minus a times sine alpha, which is omega t, and times sine beta, which is the sine phi. Now notice that a we don't really know, we need to figure it out. A times cosine phi, the both we don't is unknown. So we can just go ahead and say, well, since we haven't found it yet, we're going to call this product to be A1. Then times cosine omega t. And plus, because we don't know the number going to now is negative or plus, it doesn't matter, that a times sine phi is another unknown. And we call this unknown to be A2 times sine omega t. So this is another way of expressing that. So now what happens here then is that we want to try that solution, see if that's reasonable. And from the original differential equation, equation 1 here, we wanted to figure out what they are equal to. So we need to figure out, the first one is the di dt. Let's see what the derivative of that is. So take the derivative, di dt, and we're going to end up with a negative a1 times sine omega t. And then for the chain rule, we're going to have to take the derivative of that argument omega t with respect to t, and we end up with the omega. So we're going to insert the omega over here. And we have an omega coming out of that derivative. Same thing here, we're going to take the derivative with respect to t for the second term, a2 times sine omega t, and we have a2 cosine omega t. And then omega t take derivative with respect to t, we end up with another omega over here. Okay, so we're ready. We're going to put in the equation 1. We're going to put the equation 1, see what it look like. So the equation 1 is equal to L multiplied by the di dt, which we just worked out, and that is negative a1 times omega times sine omega t plus a2 times omega times cosine omega t. Now plus r times I, and the I is equal to a1 cosine omega t plus a2 sine omega t. And that is equal to, so I can say equal to Vm times cosine omega t. Now we examine that equation here, the equation 1, and we find out that we have a bunch of sine omega t's and cosine omega t's on the left-hand side, but everything when we add them up, it has to be equal to cosine omega t. So that means that let's gather all this sine omega t here. Let's combine the like terms. This is sine omega t, and here's another sine omega t. And then the cosine omega t here, and cosine omega t here. So let's combine the like terms. And what we have here is we have L. This is L right here. L times A2 omega plus A R times A1, that multiplied by cosine omega t. So I'm combining the cosine omega t's. Now I'm going to combine the sine omega t's. So I'm going to plus R times A2 minus L A1 times omega. That times sine omega t. And this is equal to Vm cosine omega t. So we can see here, if that is valid, then we know the coefficient of cosine omega t must be equal to Vm, where the coefficient of the sine omega t must be equal to 0, because here it basically says that this equals plus 0. So we do that. We end up with that L A2 omega plus R A1 is equal to Vm, where R A2 minus L A1 omega is equal to 0. This is the conclusion from that differential equation. Now, if they satisfy that, and we found the solution. So we're going to solve that, and I'm going to call this equation A, and that's equation B. In these two equations, what we wanted to figure out is A1 and A2. So we work that out. We have A1 is equal to R times Vm divided by R squared plus omega squared times L squared, where A2 is equal to omega L Vm divided by R squared plus omega squared times L squared. Okay. Now, remember that from the differential equation before we actually get to A1 and A2, here, we assumed the I is equal to A times cosine omega t plus phi. And equivalently, we have that expression where we find the A1 and A2. So what do we wish? We wish to go back so that we can actually find another form of that solution, which is A times cosine omega t plus phi. We want to know A and phi. Now, since we know from this conversion that A1 is equal to A times cosine phi, where A2 is equal to sine phi, and you can see clearly that if I want to know A2 equals A times sine phi, and you can see if I square on both ends, we square that, and we square the A2 as well. Then we sum them up. And we have A1 plus A2. That will be A squared cosine phi squared plus A squared times sine phi squared. That is equal to a1 squared plus a2 squared. Now you see, we know a1 and a2 already. And we also notice that if I factor the a out, we end up with cosine squared phi plus sine squared phi, and that is 1. Therefore, we can find a is equal to square root of a1 squared plus a2 squared. Now all we need to do is square that a1 and square the a2 and simplify it. We find that the a equals to vm divided by square root of r squared plus omega squared L squared. Also, from these two equations here, from this equation here and this equation here, we find a ratio. We're going to use a2 divided by a1. We end up with tangent phi is equal to a2 divided by a1. That gives us the phi is equal to inverse of tangent a2 divided by a1. So a2 is this and a1 is this. So now you can see we have this common denominators, and that would be cancelled out. And we have inside, we're going to have omega L divided by R and negative. The reason there's a negative here is that we probably remember here we absorbed negative sign in here. Right here, there's a negative sign. A negative sign in here. So a2 is negative a times sine phi. So a2 is equal to negative . All right, up to that point, we find a solution. We have